When we did our initial work with trigonometry, we limited it to right triangles. SOHCAHTOA works beautifully with right triangles, and everything is fairly simple and straightforward with right triangles, but we would also like to be able to do things with other types of triangles too. That's where the law of sines, in this section, and the law of cosines, in the next section, come in. A few chapters ago, we did work with proving triangles congruent. Do you remember the 5 ways to prove triangles congruent? Here they all are. Did you remember them all? It is important for this section to realize that HL was a specialized case. The other 4 ways worked on all triangles, but HL didn't. HL was a special case for SSA which only works on right triangles. SSA does not work on triangles that are not right triangles. The same kind of thing happens with the law of sines. It doesn't have to do with right triangles, but SSA is a specialized case here too. Triangles that follow an SSS or SAS pattern can be solved with the law of cosines. We will do those kind of triangles next section. Triangles that follow an ASA or AAS pattern can be solved with the law of sines. We will do those kind of triangles in this section. Triangles that follow an SSA pattern are a very specialized case that can sometimes be handled by the law of sines too. I'll go over the issues, and there are a lot of them, with this special case in a bit. When the law of sines is stated, it always uses a triangle that looks like this. Notice how each angle and its opposite side always use the same letter. One capitalized and one not. When we have a triangle that looks like this, then we can state the law of sines like this. All of that says in that first sentence is that we have a triangle that looks like the one below. So that's not as useful. Generally, people find the picture a lot better than that sentence. However, the thing to really remember about the law of sines is this extended proportion. The sine of A over A equals the sine of B over B equals the sine of C over C. This is how the book writes the law of sines. So that's what I did. But if you remember from our properties of proportions, we can flip these fractions upside down. Thus, this also works. You will find a lot of places write the law of sines this way instead. Just know that it is perfectly okay to do it this way. It works just as well. Use whichever you like better. This little nugget is not something you need to know at all, but it is interesting for people like me. If you write the law of sines that alternate way, like this, then each of those ratios is actually also the diameter of the circumscribed circle. Do you remember circumscribed circles? That's this guy here. So A over the sine of A, and B over the sine of B, and C over the sine of C are all the same as the diameter of that red circle. Not something you need to know, but interesting. The law of sines can be used with triangles in an ASA, AAS, or sometimes an SSA pattern. Let's look at an example of the 2 easy ones, the ASA or AAS pattern. In this triangle below, we are being asked to find an approximate value. If you didn't already know that this was a law of sines problem, that should be a huge hint that trig is going to be needed. Next, notice that this has an AAS pattern. 2 angles were given to you, plus 1 non-included side. ASA or AAS triangles both have 2 angles. The very first thing you should do for either type of triangle is fill in the missing angle. Simple so far, right? Once you notice the AAS pattern, you should immediately think to do the law of sines. This guy here. Time to fill in what we know. We can break this apart into 2 separate things. Once you have those proportions, you simply cross multiply. Remember that this problem asked us to round to the nearest tenth, so that's what I did here. This is how you would use the law of sines with ASA or AAS. Simply fill in the missing angle and then fill in the law of sines. ASA or AAS are 2 pretty easy cases. The nice thing about ASA or AAS is you know the law of sines will work and that it isn't even too hard to use. But SSA is another monster altogether. This is a geometry course. We are only giving an introduction to the law of sines. We only want to get you a little used to seeing it and give you a little practice with using it. In later math classes, you will use it some more and in more depth. There are easy SSA problems, and there are more difficult SSA problems. Here's the good news. Since this is only an introduction to the law of sines, we will only be giving you the simple, straightforward SSA problems. You won't be seeing the more difficult stuff. You don't even really need to know what the more difficult stuff entails. At this stage in the game, all you need to be able to do is notice an SSA pattern is happening and know that you need to use the law of sines to answer the question. It will always be straightforward and it won't be a problem. At least for this class it won't. You don't need to know the following at all, but I wanted to give you a taste for how onerous SSA can be and what you will be doing in future math classes when you delve more deeply into the law of sines. If I'm giving you an introduction to the law of sines, I think it would be remiss if I didn't at least show you or give you a taste of what this looks like. So, let's assume you want to build a triangle out of angle A, line segment AB, and line segment BC. That would make SSA. These are the multitude of cases that SSA can be. Doesn't this all look fun? I know you're probably sad that you won't be asked to account for all of these cases. All you have to be able to do is notice SSA is happening and apply the simple law of sines. You can save all this harder stuff for another day. I'm sure you're looking forward to it.